So we can see that if the net force in this perpendicular direction is 0, and it is because it's not accelerating up or down, that N, well, the other force opposing it is this component of the weight. The weight's pulling straight down, but it also pulls against the slope and along the slope. So the portion of the weight that's pulling against the slope must be equal and opposite to N. And now let's think about the forces in the parallel direction or in the x direction relative. So the forces, we've considered the forces perpendicular to the slope. Now let's consider the forces parallel to the slope. What is the net force parallel to the slope? Well, it's the addition of all of the forces, first of all. The forces pushing it up and down, I see two of them. There's a portion of the weight that's pulling downwards, and this is in the negative direction down the hill, so I'm going to put a negative sign there. And this guy, this man, we've decided that he's pushing down, although we don't really know. I'm going to put, force, man, question mark. And what is the net force? Is there an acceleration? And here's where we have to be careful of language. It's this piano is moving down the ramp, but it actually says that it's moving down the ramp at a constant velocity. The velocity is equal to a constant, and it gives us a value, gave me a value of 12 meters per second, but that's not relevant. Actually, what's important is that the velocity is a constant. And if the velocity is a constant, what this means is the change in velocity is 0. And what this means is the acceleration is equal to 0, because the change in velocity is 0. And since F equals ma, this means the net force is also equal to 0. So this is very much like the East Indian guy holding back a whole train of shopping carts. For those of you who were in class and saw that video, there was a guy sliding down a hill, pushing up on grocery carts, a whole chain of them. He was sliding down with constant velocity, and I argued there that he was in equilibrium. Even though he was in constant motion, the carts were pushing down on him, he was pushing up on the carts, and they moved without accelerating, and the forces were equal and opposite. He wasn't accelerating, and he was in constant motion. So that's what must be happening here. And we can see that right away mathematically, because if we realize that the net force is 0 in the parallel direction, and we put it here, and we bring weight to this side, or actually I'll bring this force to this side, the force of the man, the mysterious force of the man, I'll have negative weight parallel is equal to the force of the man. I don't know what that is, but I don't know what it is, but it's equal and opposite to the portion of the weight that's pulling down. And the portion of the weight that's pulling is this way, and he's opposite of that. So he must be equal and opposite to this weight pulling down. Because if he wasn't equal and opposite, then they would both be pushing in the same direction, and this thing would accelerate down. Because on its own, the weight is going to pull it down the hill. So if there was no guy around holding this piano, on its own, there would be an imbalance. There's no other force parallel to this slope except this portion of the weight that is parallel, and this force here would accelerate this object down the hill. So he must be pushing up the hill. This is an analogous situation to the East Indian grocer. So there's the force of the man. He's pushing against the weight, and this piano is slowly, actually this is a pretty low velocity, so he's slowly letting the piano move down the ramp, and so this piano is moving down the ramp despite him pushing back. And he's keeping it at a controlled, constant velocity. All right, I better end it there. Again,